recall that reconstruction is the process of obtaining a continuous time signal from the samples of a signal. And we said that we could do that uniquely if we sampled the original continuous time signal at least twice the highest frequency that was present in the signal. When we analyzed sampling in the frequency domain, we saw that one way to do reconstruction, at least conceptually, was to take the samples of the signal, pass them through an ideal low-pass filter, and that would result in a reconstructed signal y of t, which agreed with the samples of the original signal that was given by an infinite sum of the samples times shifted sinc functions. We called this ideal band-limited interpolation, and this is idealized reconstruction, because if you look at this expression here, this infinite sum of sinc functions, this is not something we can do in practice, because at any point in between the samples, to get the value of y of t at any point in between, in other words, at values of t that are not equal to n times cap t, we require an infinite sum of sinc functions. And of course, that's also a consequence of the fact that HLP was an ideal filter, and we can't build these kind of brick wall filters in any practical kind of system. So this is a very important problem if we are going to process signals in discrete time and convert them back to continuous time. We have to have a practical way to do reconstruction. And the way we're going to do that is using something called the zero order hold. Now what a zero order hold does is it simply takes the value of the current sample and converts it to a voltage that gets held for the duration of the sampling interval. This results in a waveform, continuous time waveform, that has a stair-step character to it. So I can sketch an example here. So if this is the value at time 0, say that's y of 0, then what the sampled value, then what I'm going to do for the continuous time waveform is I'm going to hold that value for a duration t. And then at y of 1, I have, say, this value, then I'm going to hold that. So this is 2t, and so on. So we get this stair-step behavior. Amplitude here is y of minus 1. So we get this stair-step signal, and we're going to call that y subscript 0 of t to indicate that it came from the zero order hold. And this is a very practical thing to do. We can just convert this number here, y of n, into a constant voltage and hold that until we get a new number. And then we have a clock that runs at t, and we simply convert each sample to a voltage and hold it. Okay, now this clearly is not the original signal, because the original signal was smooth, right? We had it band limited to satisfy the sampling theorem. So in terms of understanding what this has done, we can, and what we might need to do to reconstruct the original signal, we're going to describe y0 of t in terms of an equation like we had up here with the ideal interpolation, which was in sinc functions, except in this case we're just going to have rectangle functions that we're going to be adding up. So we're going to define a rectangle function h sub 0 of t, which is 1 when we're in the interval from 0 to t, as I've drawn here, and it's 0 otherwise. And using this signal, I can obtain that stair-step expression for the output of our zero order hold by just writing it as a sum from n equals minus infinity to infinity of y of n h0 of t minus nt. So this one here is h0 of t times y of n, or y of 0. Then this one becomes h0 of t minus cap t times y of 1, and so on. So this, for example, this one here, this term is y of 3 times h0 of t minus 3t. So if I add all these shifted rectangle functions up, I get that original stair-step function as the output of the zero-order hold. Now, to analyze this, we're going to write this expression here in a slightly different format, and that is we're going to recall that I can shift a function to a certain time by convolving it with an impulse. So this expression becomes y0 of t will be the sum from n equals minus infinity to infinity of y of n times the impulse shifted to time nt convolved with h0 of t. So this convolution shifts h0 to time nt, and now this is an expression that we've worked with in the past. This is equal to something we'd previously called y sub s of t, which was on the previous page as the input to that ideal low-pass filter. We did ideal reconstruction, but here we're seeing that we can get the zero-order hold by putting y sub s of t as the input to a filter whose impulse response is given by h0 of t. Of course, if we go into the frequency domain, the convolution just converts to multiplication, and we get that y0 of omega is equal to y sub s of omega times h0 of omega. And recall that the Fourier transform of the sampled signal y sub s of t was given by 1 over t times the sum L equals minus infinity to infinity of shifted replicates of the Fourier transform of the original continuous time signal. And we can calculate the Fourier transform of this rectangle, and we know it's going to involve a sinc function when we get that h0 of omega is equal to 2 times sine of omega t divided by 2, cap t, over omega. And then we have this phase shift, e to the minus j omega t over 2, which is due to the fact that this rectangle is not centered at 0, but it's actually shifted by t over 2 from 0. And so that adjusts the sinc function. It's useful to depict this graphically in order to gain some insight. So here I've sketched ys of omega, which I've assumed that y of omega is my favorite example of a rectangle, or a triangle that is, with bandwidth omega naught and unit amplitude. So then when I put that into the expression for ys of omega, we get the replicates, and this continues on at multiples of omega s. What we're going to do when we do the zero-order hold, that's equivalent to taking this signal and multiplying by h0 of omega. Now h0 is complex, so I'm going to draw a real or the magnitude and the phase. So the magnitude of h0 of omega is the magnitude of a sinc function, and the zero crossings occur at omega sub s. The phase of h0 of omega is just a linear function because we had that linear phase term e to the minus j omega t over 2. And the slope of that is such that it goes from pi at minus omega s to minus pi at omega sub s, since omega s is 2 pi over t. And then because there's a zero crossing in the sinc function, the phase jumps by a factor of pi at omega sub s and at minus omega sub s and multiples thereof. So if we look at the result of multiplying our original signal spectrum, which in general is complex, but I'm just showing it as a purely real function here, times this, and I'm just going to sketch the magnitude, we see that the magnitude of y0, the output of the zero-order hold, how it corresponds to the spectrum of the original signal, which is what we're trying to reconstruct. In the primary part of the spectrum, we have some distortion, which is due to the curvature of h0 of omega, and then out at multiples of omega sub s, we see we have some residual spectral content or residual energy, which is due to the fact that this zero crossing here has non-zero values to the right and to the left, and those are going to interact with the spectrum of the sampled signal. The same kind of thing happens at 2 omega sub s and 3 omega sub s and on up. And that explains the sharp character, the stair-step character of a time domain signal, which to have those sharp edges, we need higher frequency components in the spectrum. And so those are there at multiples of omega sub s. So clearly, the spectrum of the output of the zero-order hole does not match the spectrum of the original signal. We have a little bit of work to do yet to reconstruct this original signal. Oh, I also forgot to mention when I graphed H0 that the magnitude at omega equals 0 is t, so that does compensate for the 1 over t that was in ys of omega. So we're going to list the effects of the zero-order hole that we just looked at in this example. So we had a linear phase shift, which I wasn't able to draw in the final result, but that corresponds to a time delay of capital T over 2. The second effect is that we had distortion we saw in the spectrum in the bandwidth of the signal, which was from minus omega naught to plus omega naught, and that was due to the curvature of the main lobe of H naught, H0 of omega. And finally, we had these distorted and attenuated replicates of the original signal spectrum that were located at multiples of the sampling frequency. So these were the three effects of the zero-order hold, and this is why the time domain signal has this stair-step behavior and doesn't really look like the original signal that we probably sampled. So we can correct some of these effects. We can't correct number one because the time delay, to reverse that, we'd have to have a time advance, and that's a non-causal operation. So in a practical system, once a time delay is introduced, we can't fix that. So we're going to have to live with that one. But these other effects, we can do some subsequent processing to get rid of them. And what we're going to do is use something called an anti-imaging filter. We'll call this filter HR of omega. And to correct the effects of 2 and 3, what the magnitude of this filter has to satisfy is something like the following set of constraints. So in the passband, we have to undo the curvature that was introduced by the sinc function, and then we want to get rid of those replicates of the spectrum that are at higher frequencies. And the first place they start is omega sub s, the sampling frequency, minus omega naught. So if I force this to be 0 out here, and in the passband, or in the bandwidth of the signal, we'll have 1 over the sinc function, that H0 of omega. And then in this interval here, and this is what makes this a practical system, is that between omega naught and omega sub s minus omega naught, in this interval, there's no energy in y0 of omega, so we really don't care what the filter does in here. So our anti-imaging filter is a low-pass filter with ideally that has this sort of inverted sinc main lobe curvature in the passband, and then is 0 out at higher frequencies. Well, I see a mistake here in what I originally wrote down for the sinc function. There's a factor of 2 missing from the denominator, so we'll write that in there and make that sure that the amplitude of that sinc function is correct. So we put our zero-order hold together with this anti-imaging filter to get our practical reconstruction system, which looks like something like this. And basically what's happening here is we take the values, the numbers, y of n, in discrete time, and each of those numbers gets held for the duration of a sampling interval from cap t seconds in duration to produce a stair-step signal y0 of t, and then we apply a low-pass filter, HR of omega, which is an analog filter, so this is made with capacitors and resistors and active components and so on, to smooth out the sharp edges in y0 of t and give us y of t. Our goal, when we design our low-pass filter, we want to have the product of the anti-imaging filter and the zero-order hold in the frequency domain to correspond to t for frequencies within the bandwidth of the original signal, and that'll reconstruct that part of the signal between minus omega naught, and And then we need to have it be 0 for frequencies greater than omega s minus omega naught, and that'll get rid of the replicates that show up at multiples of omega s at the output of the zero-order hold. And in between here, we really don't care what happens. Now, as an analog filter, the degree of difficulty in building this filter is determined by the size of this region in here where we don't care, because we have to transition from a pass band to the stop band of the filter. And doing that suddenly is quite difficult. Doing it over a wide frequency range is much easier. So I'm just going to write for now, we're not going to cover analog filter design, but that the bigger that transition band, the better. And that occurs when the sampling frequency is significantly higher than the bandwidth of the original signal. And we'll come back to this point when we talk about oversampling, upsampling, and downsampling, and how that's used to reduce the constraints or simplify the constraints on the analog filters and make them less expensive to build. But for now, this is our practical reconstruction system. Basically, are going to hold the voltage for the duration of the sampling interval, length capital T, and then come up with a low-pass filter that smooths out that stair-step function.